This video will help you learn how to solve limiting reactant equations. Many students have trouble with chemistry equations mainly because they can't relate it to things that they've known from previous years. And this is not uncommon. Many students have this problem. And with this video, I'm really hoping to help you understand how to solve limiting reactant equations. When you break down limiting reactants down to their basic definition, stoichiometry is really nothing more than a fancy chemistry word. Whenever you're baking a cake, you call it a recipe. If you're solving a math question, it's equation. Whatever you want to call it, stoichiometry is nothing more than the ratio between items you put in to items that you get out. A very simple explanation for what a limiting reactant problem is when you think about placing quarters into a vending machine. Whenever you put 2 quarters in, you get a drink back. And then for every 2 quarters beyond that, you get another drink. But if you only put in 1 quarter, you will not get a drink back no matter how much you want it. A way to make things a little more complicated is to have 2 reactants giving you 1 product. For instance, when you put a gas and key into a car, the car will operate. For each car operated, a person would need 1 key and 1 tank of gas. So if some guy named Jack had 5 car keys and 4 tanks of gas, would keys or gas tanks keep him from operating cars? Which one would be the limiting reactants? Well, gas tanks. After operating 4 cars, he's going to be out of gas. Now, to put a little bit of a baker's twist to limiting reactants is to kind of look at making a pizza. For whenever you make a pizza, you have to start with a lot of ingredients. You need a pizza crust, about a cup of cheese, 8 pepperonis, 2 cups of pizza sauce, and this is going to give you 1 pizza. So, hypothetically, if you're a pizza worker and you're making pizzas and you have to make 5 pizzas, you might be kind of worried when you're looking at your ingredients. Because even if you have plenty of crust and sauce and you only have 4 dozen pepperonis and 2 pints of cheese, will you have enough to make all of your pizzas? Well, it'll be your limiting reactant. Well, the first thing you need to do is write down what you need to know. The number of pizzas. Write down what the question gives you, which is 4 dozen pepperonis and 2 pints of cheese. Then the conversion into the terms that are given to you in the equation, so 12 pepperonis per dozen and 2 cups per pint. Use the mole-to-mole ratio that you can get from the equation, and when you multiply across, 4 times 12 times divided by 8 is 6, and 2 times 2 is 4. When with 4 pizzas, that makes cheese the limiting reactant, because you're going to run out of cheese at 4 pizzas. Okay, so now let's look at it with adding a little bit of chemicals. So P4 solid plus 6Cl2 gas yields 4 PCl3 liquid. And what this kind of means is that for every P4 that you put in with 6Cl2, you're going to get 4 PCl3s. So if you have 3 moles of P4 and 21 moles of Cl2, how many moles of PCl3 will be formed? So you write down what you want to know, the number of moles of PCl3, what you're given, 3 moles and 21 moles, you multiply it by the mole-to-mole ratio given to you in the chemical equation, and then when you multiply out across, 3 times 4 is 12, and 21 times 4 divided by 6 is 14. So because 12 is less than 14, that means the limiting reactant is P4, because you're going to run out of P4 first, leaving excess Cl2. So now that you kind of understand how limiting reactants work, the rest of this video I'm just going to go over a couple of old midterm questions just so you can kind of know what to be expecting for your test. In the balanced equation below, how many grams of solid iron can be formed if 50 grams of Fe2O3 reacts with 10 grams of carbon monoxide? Pause the video real quick just to see if you can solve this question on your own, and then resume the video to check your answer. Alright, with all the other examples, the first thing you want to do is write down what you need to know, the number of grams of iron. Write down what you're given, 50 grams of Fe2O3 and 10 grams of carbon monoxide. Then you're going to divide it by the molar masses for these 2 chemicals that you get from the periodic table. You're going to multiply them by the mole-to-mole ratios that you get from the chemical equation. And then you're going to multiply it by the molar mass of iron that you get from the periodic table. And then when you multiply out across, you're going to end up getting 35 grams of iron and 13.3 grams of iron. So since 13.3 is less than 35, that means carbon monoxide is the limiting reactant. Because when you make 13.3 grams of iron, there's not going to be any carbon monoxide left. And with no carbon monoxide left, no more iron can be formed. Therefore, 13.3 grams of iron is the correct answer. What mass of calcium carbonate is formed when 25 milliliters of 0.12 molarity calcium nitrate is mixed with 30 milliliters of 0.11 molarity potassium carbonate? Well, with this kind of question, the first thing you need to do is write down the balanced equation. And if you know your polyatomic ions, you'll know that calcium nitrate is CaNO3 and potassium carbonate is K2CO3. To find out what's on the other side of the equation, you need to switch ionic partners, which will give you calcium carbonate and potassium nitrate. And then to balance your equation, you need to put a 2 in front of potassium nitrate. Pause the video real quick and see if you can finish this question on your own, and then resume the video to check your answer. Alright, so the first thing you need to do is write down what you're looking for, the number of grams of calcium carbonate. And then you write down the measured quantity given to you in the equation, so the 25 milliliters and the 30 milliliters. And then you need to use your molarity as a conversion factor, which milliliters is 1 times 10 to the third liters, and that's going to be in the denominator. And then the given molarity goes on top for moles, because molarity is moles per liter. And then you're going to put in your mole to mole ratios that you get from the chemical equation. And then you use the periodic table to find the molecular mass of calcium carbonate. And when you multiply out across, you're going to get 0.300 grams of calcium carbonate and 0.330 grams of calcium carbonate. And because calcium nitrate has a lower theoretical yield, it creates less calcium carbonate. It's going to be the limiting reactant, and therefore the mass of calcium carbonate is 0.3 grams.
There's antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium and manganese and mercurium, molybdenum, magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium and tantalum, technetium, titanium, tellurium and cadmium and calcium and chromium and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard, and there may be many others, but they haven't been discovered.